Yeah, okay, good. So let's start. So welcome to the last Israeli algorithmic game theory seminar for this semester. So we're delighted to have Scott Kominers talking about infinity and beyond. So welcome, Scott.
Awesome. Thank you so much for having me. I'm, as I was saying right before we started, I'm very honored to be there and do wish I could be seeing all of you guys in person. Although I continue to be amazed and impressed at all of the opportunities that this, remote technology creates for, new opportunities to see and speak with people. I'm very excited to be presenting this particular paper in this seminar because it's really, Israeli in in Genesis. The unintentional pun, was not intending to pun off of Genesis, but it's joint work with Yanai Goncharovsky and Ron Shore, and it really sort of came out of both of theirs and especially Ron's experience, like studying logic alongside all of the other parts of rationality and choice and economic theory in Israel. And so I'm very sort of pleased to have been along for the ride with these two extraordinary co-authors. You should apportion far more than 2/3 of the credit to them. So I'm presenting, but have them in your in your mind's eye as we're working through the material. I'm also very excited. This is the first time I have ever presented simultaneously for all the major universities in Israel, as the website, demarcates, which is pretty cool. And I unioned that with the MSR set because I saw one of the organizers is Moshe. So, all right. Oh, and please ask questions, in real time. I'll be monitoring the chat while we're talking, and also just feel free to shout out. I'd much rather, have a conversation than just be standing here lecturing or sitting here lecturing. Okay, so what is this paper? This is a paper that sort of looks at the edges and, sort of structure of economic models. One more caveat, which is that I've spent the last 5 days dealing with a bunch of housing chaos, which means I have not slept particularly well. So, feel free to tell me whatever I'm saying is unclear, or whatever. I'll do my best to clarify. But this is my essentially first academic activity in 5 days of very little sleep, so it could easily be sort of way less clear than usual. Fine. This is a paper about the edges and and boundaries of economic models. And I mean that sort of literally in addition to figuratively. So a lot of models throughout theory assume finiteness in some way. Maybe there's a finite set of agents. Lots of game theoretic models also have a finite time horizon. Or even if they have an infinite time horizon, like in many repeated games models, there's a start date. So there's a finite past horizon, even though there's an infinite future. And then in decision theory, we often work with finite data sets instead of infinite ones. And again, these are sort of, these are assumptions that are made for simplicity. And they don't seem obviously unnatural because a lot of things in the world are in fact finite, right? The set of people in the world is finite. If I start playing a game with you today, it had a finite past horizon, even if we continue to play it infinitely into the future. And in fact, it even has a finite end date because, at some point, one of us or both of us will cease to be able to play the game for whatever reason. And in practice, usually we only have finite data rather than infinite data. But by the same token, these assumptions play a real role in the analysis in ways that we think, might make the analysis less general, or in particular, the theory we study, or the theory we build might explicitly rely on finiteness in a way that makes it sort of, more of the consequence of an edge effect or some other component of the math rather than sort of the underlying, sort of concepts and conceptual ideas. So we often think of, models without finiteness as more robust or better representations of limits. And I'll give a couple examples of that in a moment. But let me quickly note that, like, finiteness assumptions really do play a role in the analysis, in the sense that when we drop it, if we can drop it as an assumption, we often have to either retrace the entire argument with new detail, or the finite case argument with new detail to get the infinite case, or introduce some completely new, like very different and very elaborate arguments. So, in the world, the world I live in the most frequently, the world of stable matching, Gale and Shapley give an explicit algorithm, deferred acceptance, which my guess is probably, all or nearly all of the people in the seminar are, deeply familiar with, for finding stable matchings. When you want to extend this to infinite markets, the math changes a lot. You actually need to think about the matching process as some sort of fixed point algorithm, and then you use like a theorem that picks out fixed points, and so the generalization of Gale and Shapley, like the direct generalization of Gale and Shapley, that Tomasz Fleiner put together first, uses a very different structure, and is a little bit existential. It's pulling stable matchings out of a fixed point process. What we're going to do today is give a unified and we like to say user-friendly method for lifting finite model results to infinite ones, using the theory of what's called logical compactness. And I'll say what that is in a moment, but first let me just quickly, give a little bit more detail to why we think that these infinite models are actually going to matter. So as I said, like everything is finite in practice, and usually. So there's a sense in which infinite models are abstractions, but we think in economics that these are often like the right abstraction. For example, if we think about an infinite set of agents, we think of this as sort of like, representing what happens in a limit market, or or some sort of average case. And we do this explicitly, right? We talk about large market models as a representation of a large market, and to do this, we usually assume either like a countably infinite or a continuum of agents. And there's also a sense in which these are sort of less susceptible to frictions. Like some results use the use the finiteness of the set of agents in a way that if you start like adding more agents, the result might sort of or if you pass to a large market limit, the result breaks down. In the context of infinite time horizons, we think of the infinite past horizon, sort of as you're adding that in as better incorporating a dynamic steady state, right? If you want to think about like how a game works in steady state equilibrium, you want to understand like how, you want to sort of reflect on it as if it never had a start date, right? You sort of like think of this as an equilibrium that's just persistent and ongoing. And for this, if your construction of your equilibrium relies on there being a day zero, we worry that, like, again, we sort of might not be capturing the right phenomenon. And then lastly, there's this question of infinite data sets, which I won't talk about very much today. I'm going to stay mostly in these top two, but I'll assuming there's time, state a theorem on the data sets as well. Being able to theorize about an infinite data set lets us sort of differentiate between the impact of finiteness of the data and inherent limitations in what we can observe from all choices. And so there's a real sense in which, again, like the infinite data set is an abstraction, but it might be the right abstraction, right? We want to understand in choice theory is like, what can we possibly infer from choice observations? Not, what can we infer from choice observations, like in this weird, like edgy context where, the choice observation is always finite. Okay, so that's the like, basic motivation and framing. In a second, I'm gonna, sort of give loose and then formal statements of the model and models and setup. So let me pause there for a second and see if there are any questions. Going once. Going twice. Sold. All right. So logical compactness. What is that? That's going to be our hero the entire day. And logical compactness is exactly as it sounds, a topological statement about formal logic. It says that logic is compact. So that's a little bit of a, we're doing math on math. More precisely, and again, I'll do this with notation in a moment, but what it says is that a set of logical statements can be made true simultaneously if and only if every finite subset can. And so this naturally looks like a compactness statement, right? It's like, we can, it's a relationship between a potentially infinite set and finite subsets. What we're going to do with it, it's not at all obvious, as I've stated this, how this has anything to do with game theory. What we're going to do with it is rephrase a number of different classical models into logic, and then, in ways that their infinite, variants correspond, to, to a set of infinite logical statements. And then we're going to look at their projections to finite subsets of those statements, and show how to, how to use the original models to make those finite subsets true. And that, by logical compactness, is going to imply the infinite case. There's a bonus from working this way. It's a bit existential, right? Like we're going to use instead of doing topology on our models, we're going to use topology on the math we use to phrase our models, in some sense. But it has a bonus, which is that it's going to let us reason about the finite models in their original language, rather than like explicitly modeling anything that looks like, or explicitly analyzing anything that looks like a limiting process or convergence or something of the sort. All right. So where are we going today? I'm going to do a quick crash course in propositional logic. And then, most of the talk, we're going to work through different examples of matching in infinite markets. We'll do a warm up where we reprove, not Tarski's theorem, sorry, Fleiner's theorem of, existence of stable matching without using Tarski's theorem. And then we'll talk about structure and incentives results. And then I'll show you how you can use the same techniques to address a question in couples matching. Then we'll briefly skim over the other three settings we cover in the paper. So one of the cool things about this logical compactness machinery is you can sort of use it independently across lots of different settings. So we'll show you how to use it in a context of stable matching with a time horizon, sort of like a simple dynamic stable matching model, and then how to get Walrasian equilibria in infinite trading networks. And finally, if there's time, I'll state an example of a theorem we can prove in this context, in choice theory, and then wrap up. Cool. All right, another good place to pause for questions. We've set out the roadmap. We're about to go down the road. Questions? All right. Rock and roll. So, propositional logic. Oh gosh, I think this is going to have the same typo. There's one typo that I suspect will persist, which is that matched MW, the M's and W will switch around. The M is supposed to be a man, the woman is supposed to be a W. Long story, I keep trying to fix versions of this and then like adjusting based on earlier, sort of different versions of my slide deck, and it keeps creeping back in. I'm really sorry. Anyhow, we're going to define a set of Boolean variables. The good news is they're existential variables, right? They're just Boolean variables. They happen to be named matched WM or soon to be matched MW, but like that's just a variable name. For a given set of Boolean variables, the set of well-formed propositional formulae is going to be defined inductively off of those variables. So we start with all of the quote unquote atomic formulae. Those are the variables that we started with. And then for every formula in the set, we add in a not option. So not formula for every well-formed formula. And then also for every pair of formulae, we add a, or, and, implies, and, sort of equals, like a if and only if. Now note, if I start with a finite variable and I start inductively constructing these formulae, every formula, there will be infinitely many formulae, right? Like, for any two of them, I can create a new one by taking their join or their meet. But every such formula is individually itself finite. So this is a, countably infinite set of, not necessarily countable because the underlying formula, the underlying atomic formula might not be countable, but it's an inductively, it's like an indexed inductively, sort of constructed set of formulae. And every individual formula is going to be finite. So if we call our original variable, see, I told you it's going to switch to MW. My apologies. It's an unordered pair, even though it looks like an ordered pair, we'll call it. So if we start with matched MW, we're going to have a new, you can have a new formula that's called, the one variable is going to be matched MW, another one's going to be matched MW prime. An appropriate formula might be matched MW implies not matched MW prime. Now, of course, this is, again, just a statement in Boolean logic. But once we switch to matching in a moment, this is going to have a natural sort of semantic interpretation, which is that we're saying if M and W are matched to each other, then M had better not be matched to some other W prime. A model is a mapping from variables to Boolean values, and we say that the truth value of a formula in a model is defined inductively. It's given in the way you expect. It's like, is this formula true in Boolean logic? Any questions here? All right. So what is logical compactness? A set of formula is satisfiable in the sense that there is a model in which all the formulae are true, if and only if every finite subset is satisfiable. So if I give you a potentially infinite set of these formulae, and I want to know, is there a way of assigning the variables so that all the formulae are true at once? All I have to check, again, check, is whether every finite subset of those formulae is satisfiable at once. And note, it doesn't have to be the same set of truth values that satisfy each finite subset. It suffices for there to exist a solution for each one. It doesn't sort of have to patch together into the solution of the infinite set. So now let's talk about the existence of stable matchings, near and dear to my heart, and I know to some of yours as well. Not to mention of the agents we're matching. We'll imagine a set of men M and a set of women W. We're going to give them preference lists, and here the preference, actually a little bit of the subtlety is in what the preference object is. So we're going to have the agents list nth choice partners. So there has to be like a most preferred partner, but there could be agents could want a potentially infinite set of potential partners. A matching is going to be a one-to-one mapping between men and women. Potentially leaving some unmatched. So you keep this option of potentially being unmatched, matching to a null option. And a matching, we're going to say that a matching is blocked by a man and woman, M and W, if they mutually prefer each other to their assigned match partners. And a matching is stable, of course, if it is not blocked. So the classical theorem of Gale and Shapley, 1962, shows that stable matchings exist in finite markets. And as I mentioned, and again, I'm sure most of you guys, think of as bread and butter, whatever the appropriate Israeli metaphor is. It's a very, very well-known construction. It's deferred acceptance. You have each man propose to his first choice woman. Women hold their best acceptable proposals, reject all the others. Rejected men propose to their second choices, and so forth.
So, Scott, if I may ask something, preferences, so that you assume that the set of men that a woman prefers to a fixed man is always finite.
Yes. That's gonna turn out to be very important.
That's the restriction of preferences, because it doesn't have to be this way.
It's true, although it's
that. For example, I could have all women. First, I rank all women above height a certain height. They are all strictly preferred to all women below a certain height, but inside I have preferences. So if I take one woman, and there may be infinitely many women which I prefer to that woman. So it is a restriction on preferences.
Yeah, totally. That's definitely right. It's not entirely, I wonder.
Now, maybe you can handle that also, but I was trying to understand what if you know, what restrictions is puts on preferences as of now. But
yeah, no, exactly. So first of all, you're correct, right? And it's going to use very, you know, the argument is going to use pretty explicitly the fact that like the upper set is finite.
It's finite. It's always finite. Exactly.
Yep. I'm trying to figure out how well posed the stable matching question is in that sort of like essentially like a multi-chain context. I'm not totally sure, but I'll have to think about it.
I mean, maybe there is a way to get rid of it, like I don't know. I mean, but there may be others which are you know, very complex, so I don't know. But okay.
No, exactly.
Go. I mean, I don't want to take you astray. Just wanted to make sure I'm following.
No. You've totally got it. And it's that's a really interesting example because it gives a countable grading over infinite sets. In that particular case, I wonder whether a version of our method would basically end up placing everyone into a height class pairing and then using the same argument. So it's possible we might be able to solve that one too, but I'm not totally sure. I'll have to think about it. It's a really intriguing example. Like a lot of the like just sort of two-sided infinite preference, you're sort of like two-sided infinite preference cases we've thought about are sort of like, you know, are less rich and make the matching problem sort of ill-posed. That what you've described sounds like it might be well-posed and actually like also possibly covered by the machinery. So it's really interesting. Thank you. Great. Further questions? All right. So as you know, as we've already seen, there's this you know, sort of small subtlety in the way, you know, this is just not quite the way you normally write this down. You know, usually preferences are like strict ranking of the you know, the agent side, the other side of the market. You were a little bit more casual. The reason for the lack of you know, the reason for the like formality or lack of colloquialism is that we want to set this up so that the set of men and women can potentially be infinite. And so, you know, this model, as I framed it here, is going to make just as much sense if M and W are infinite as if they're finite. As I already mentioned, Fleiner proved the existence of stable matchings in that model. We're going to now give, but it's a you know, it's a subtle paper, right? You know, it's actually it's in some sense one of the most mathematically complex papers that has been written in generalized matching theory, and it really sort of showed the power of this Tarski approach. But you know, the dual is it's a very different language and different type of reasoning. We're gonna here, I guess, also use a different language, but give a concise logical proof that can fit on a single slide. So as I already hinted, we you know, we're going to introduce formulae that, you know, use the variables matched MW or WM. Again, see typo of, you know, ordering flip. And the first one was this example I quoted you. So matched MW implies not matched MW prime. This is, again, a statement just in Boolean logic, but what does the statement mean? It says, if M and W are matched to each other, then it had better not be the case that M is matched to W prime. So this is the this is expressing sort of one-to-oneness on the men's side, and similarly, we'll introduce a formula like this on the women's side. We'll also add a not matched MW for any M and W that don't mutually rank each other. So if M and W, you know, so if one of M or W finds the other one an unacceptable partner, we're going to introduce a not and say, like, you know, it had better not be the case that M and W are matched to each other. And then last, and here's the complicated formula, we're going to express this idea that, you know, of blocking by saying, if M and W are not matched, then it had better be the case that either at least one of them has a partner they prefer. So either matched M, W1 through, or, you know, sort of matched M through WL for some W1 through WL that's preferred, or, you know, woman W has a partner M1 matched M1 through MK that she prefers. And this exactly is where we're using the finiteness of this upper preference set, because that, it might be a very large formula, but it's always a finite formula so long as you have a highest choice. So note that I've, sort of like, these are just like logical formulae, but note that if I can satisfy all of them at once, I've actually sort of proven the existence of a stable matching, because, if you just match the men and women to, sort of who have the true, Yuval, I'll catch you in one sec, who have the, whose variables are true, then it's going to satisfy all the matching constraints. It's going to, sort of ensure that no one has more than one partner, no one who's finds each other, sort of unacceptable or matched, and, last, there are no blocks. Yuval, go for it.
Hi, sorry, just a quick question to make sure I got it right.
Please.
The preference is a list of, one is preferred to all the rest. It's a finite list, and then there is like the last place for all the rest. Like I prefer W1 to W2 to WL, and then all the rest are least preferred than anything on top of the list. Did I get it right, or is it just a Boolean of do I like you or do I don't like you?
No, it's actually it's something in between the two things you just described. So it's actually, think of it as like just a rank order list that could be an infinite list. So it's like, this person is my most preferred, this person is my second most preferred, this person is my third most preferred, and so forth, out to count potentially, sort of infinity. However, the key is, if I ask you, who do you like more than your, than woman W, who's maybe your 17th choice, there are only 16 women that man M prefers to woman W.
Okay.
And so the upper set is always finite, but the set of agents you might list rather can be infinite.
Scott, sorry. How do you know that once you satisfy that there is a matching? Why don't you? So first of all, you are missing something, because the empty matching, nobody's matched to anybody, I think satisfies everything, or not?
No, so the empty matching will have some blocks.
No, the first bullet, but why can't you have something like, the Hilbert Hotel kind of thing, that you are not matched to one, that you are not somehow, at the end, you don't find somebody to which you can match him. I don't know. I mean, I'm not.
No. So you can actually have the Hilbert Hotel sort of effect, and there's so my former student Ravi Jagadisan wrote a beautiful paper that shows, in fact, that in these infinite matching markets, you can have the Hilbert Hotel in a way that breaks the rural hospitals theorem. So you can have two different stable matchings in which, one of which in which a given man is matched, and the other one in which he's not, unlike in finite markets. And precisely the reason this happens is the Hilbert Hotel. So in one, like, each man gets their top choice and the women get their second choice, and the other one, each woman gets her first choice and the men get their second choices. And the way this involves sort of everyone moving down the line one, and this first man at the start, becomes unmatched. So that's possible. So that's totally possible here.
But I'm worried about something more basic. Having satisfied all these formulas, can you find the matching? Can you tell me who is matched? I mean, not tell me,
yes.
Of course. I mean, does it follow that for every M there is a W to which it is matched?
Oh, no, not necessarily. So agents could be unmatched. So it's possible that for some M, matched WM is false for all W.
Okay, it's like below the line, it's the same thing as you get that in finite markets, but somehow I'm still worried about something which I can't put my finger on, but go on, I'll think about it. Okay,
so let me just quickly, sort of give a slightly different statement of how we extract the matching, or we correspond the matching to these logical statements. So what we're going to do is we're going to, for every matched MW that is true, we're going to say match M and W. And as I said, it's possible that agents might be unmatched. So if matched MW is false, for some M, if matched MW is false for all W, that M just remains unmatched in the eventual matching. And to confirm for ourselves that if we did this, we're going to actually have a stable match, we have a bunch of questions to ask. We ask, okay, is it really one-to-one? And the answer is yes, because of, these two statements, right? The question is, if I, matched man M and woman W, might either of them be matched to some other partner? Well, no, because then I would fail either, one or both of those statements. And then it's like, is anyone matched to someone they find unacceptable? So is the matching I've just extracted individually rational? Well, we ask, are there any M and W that are mutually, that don't rank each other so that at least one finds the other unacceptable, that are matched to each other? Well, no, because, we had this statement, not matched MW in all such cases, and we know that all the statements in our list are true. And then lastly, like, are there any blocks? Is there are there a pair M and W who mutually prefer each other to their assigned match? And the answer again, it better be no, because if they did, we'd fail this last statement, right? So we know that they are not matched to each other. If they mutually prefer each other to their assigned matches, then it must be the case that neither, neither of them has one of these matches that they prefer, which would cause this statement to fail. And so if we can find a set of assignments for the matched MW variables that make all of these statements true at once, then we in fact have a stable matching. I claim that from that correspondence, we're actually done. And why is that? Well, every finite subset of these statements corresponds to a subset of the statements that define stable matching for a finite matching market, right? If I take any sort of finite subset of these statements and union the full set of men and women, that are mentioned in all of them, that's a finite set. I can now apply Gale-Shapley in that market to find a stable matching. And in particular, every stable matching must satisfy all of these logical statements. So I found a solution in the finite case. Logical compactness says I'm done. I have found a solution for every finite submarket, or for every finite subset of the statements. Now I have a solution for the infinite set. Although again, as I said, it's a little existential. I don't precisely know what that solution is. I just know it exists.
Scott, may I ask you a question?
Please.
So about the last formula, could it not be that M and W are not matched, and they mutually don't rank each other, and then this condition doesn't have to be true for the matching to be stable? I mean,
not match. I see. Sorry. Yes. So this is for every M and W. You're right. You should have an additional, like, for all M and W who do rank each other or something of the sort. That's right. So otherwise we'd have this be true, and then this would need to be infinite. That essentially, like, you'd have the full list. You're totally right. Should have this additional condition, that additional condition right there. Great catch. Thank you. I wonder if we have it. That actually might also be a typo in the paper. I don't remember whether I compressed that by accident when I was squishing this onto the slide, or whether whether we're actually missing that condition in our substatements. Thank you. I will definitely check that. The other cool thing about virtual talks is there are these recordings, so that I don't have to take notes. I can just go back and I could review and figure out whether sort of how I could improve the talk and how I could improve the paper and get all the questions. So thank you very much. Okay, what was I? Oh, right. So we've sidestepped Tarski's fixed point theorem, and note that once we formulated the logical formulation, that was the formulation of it was actually kind of subtle. But once we did that, the argument was very fast. We sort of just invoked Gale-Shapley. We used the language of the results in the finite markets, and that immediately gives us this lifting to the infinite markets. That's the warm-up. I'm now going to show you sort of how to do more complicated things with this approach.
Just,
yeah, go for it. Please.
The Fleiner proof, you said went through Tarski. So essentially it was going through the Gale-Shapley algorithm and trying to do it in infinite space. Was that the idea?
In some sense, so it's also not quite right. So it's true. I didn't mention. So Gale-Shapley's deferred acceptance, of course, relies on there being an end step. So if you try to run deferred acceptance in one of these infinite markets, it might never actually terminate, and so you don't actually, it's difficult to figure out whether you sort of like got into a stable matching, because usually the way we analyze deferred acceptance is we look at the, sort of the outcome you get at termination. Here, you sort of like can have infinitely many steps in which a given agent's match partner changes. And so there's not, there's not quite the same structure. The Tarski approaches in the infinite markets, in some sense, are taking the limit of that process. So there is a sense in which they represent like a limit of deferred acceptance. But it's but it is a limit. Like it's not exactly like running deferred acceptance directly. It's like think of it like more category theoretically almost. It's like, this is the object at the end of the deferred acceptance chain somehow.
Yeah. So that's okay. No, look, I mean, your approach is much simpler. Clearly, just I wanted to make to know what.
No, it makes perfect sense. And Fleiner's approach here has the advantage that it's constructive, right? It tells you, constructive in as much as a fixed point out, sort of limit can be constructive.
Yes, transfinite induction constructive, but that's we can live with that.
Exactly right. Like, I'm glad to be on a seminar where we can live with transfinite induction as a constructive approach, I must say. This is one of the lovely things about giving talks in or virtually in Israeli universities. You guys appreciate, you sort of you have the right mathematical sort of tastes. Okay, so I mentioned, so we need to do some some creativity and some lifting to get the formula, but we can do a lot of stuff with it. So we just reproved the existence of stable matchings in infinite markets. It turns out we can generalize a version of this approach to reprove the man-optimal the existence of man-optimal stable matchings in infinite markets. And then we can actually take this one step further and use it to prove that the man-optimal stable matching mechanism is strategy-proof in this infinite market context. And this is like a little bit of a, sort of surprising result, or at least it was for us when we started, because this seems very far from an existence result, right?
You mean strategy proof for both men and women? That's what you mean?
No, sorry. Same, the usual strategy proof result. So strategy proof for the proposing side, in this case, the men.
Sorry, so what's new here?
Well, previously we had no way to even, previously we didn't know how to prove this in an infinite context.
New result in the infinite case, you mean?
Correct.
Okay, sorry. I thought that you got something. Okay, something in the
infinite. Oh no, I mean that would be a complete miracle, right? So
in the finite case.
Right. It would be an amazing limiting miracle if somehow the market rounded in a way that made it strategy proof for both sides as you pass to the limit. Indeed, there is sort of we do have versions, there are versions of that theorem for
there are theorems that are true in the limit are not true for any finite approximation. So that's fine. You can get. I mean, there is nothing illogical in getting such a result, but that's not it. So go on.
Correct. No, that's right. And as I say, there are such results, but if you're willing to take a stand on sort of some structure to the preference distribution. So we know there's this large body of work that Imrlikya and Madian and Kojima and Pathak started that asks the question of sort of given this sort of for a given structure of a stable matching market, how many stable matchings are there in a large market limit? The number of stable matchings gets small, which means the scope for manipulation decreases as well. This is going to be a very different sort of infinite market result. It's going to be sort of more a direct analog of the classical sort of one-sided strategy proofness result, but lifted to an infinite setting with no structure on the preferences other than what we already had. So how do we get there? So like before, we're going to be invoking the finite market result, which is Dubin, Friedman, and and Roth. In any possibly infinite matching market, the man-optimal stable matching mechanism is going to be strategy proof for the men. And what do? We're going to sort of this feels very far from an existence result, but we're sort of going to convert it into something that's a little bit more like an existence result. So imagine, up now a possibly infinite matching market. And here's a version of a claim or lemma that appears in a lot of strategy-proofness proofs for, unstable matching. If a given man, M tilde, can manipulate to match with some woman, W tilde, then M tilde had better do at least as well by reporting truthfully. Now, this implies strategy-proofness because it says that, like, if you have some manipulation, it can't be as good for you as if you tell the truth. It turns out that it's without loss of generality to just prove this claim under the, in the case where M tilde, sort of manipulates in a very specific way. He just submits W tilde as preferred to the empty set. The reason being that, like, if he, under some preference revelation, he ends up with W tilde, this will also get him to W tilde, and you can prove that quickly. So let's call the associated outcome when he submits W tilde as preferred to the empty set mu. And we're now going to introduce a slight extension of the formulae we had before. So we're going to use those same formulae, but with a new one that says, that M tilde has got to be matched to a woman he prefers weakly to W tilde. Right. So this now adds this additional, is going to, you can see it has the structure of this, like, does at least as well. But we haven't said anything about, reports yet, right? We're just asking, like, does he do at least as well? If I restrict to, interesting, there we go, sorry. If I restrict to a finite subset of these now infinite formulae, so we had the same infinite set we had before plus one, so it's still, still infinite. But if I take any finite subset, it's going to mention, at most, a finite set of men and women, M prime and W prime. We're not going to look at just that restriction. So before we just looked at that submarket, we're actually going to look at now the submarket that contains M prime, M tilde, all the men who are matched to women in W prime under this mu object, and analogously W prime, W tilde, and all the men who are matched, all the women who are matched to men under mu. I claim that in this finite market, the man-optimal stable matching with respect to M tilde's true preferences is actually going to satisfy the finite subset of statements. So this, this formula. And note, by moving around the set of M's preferences, switching back and forth between the true preferences and this W tilde preferred to null, I'm also telling you how well he would do under a manipulation. So how do we prove that the man-optimal stable matching with respect to these true preferences is going to satisfy the finite subset of statements? Well, first of all, it's very quick to check that the restriction of mu to this finite submarket is going to remain stable under these manipulated preferences. So if M tilde submits W tilde, M tilde, why is that going to happen? Well, M tilde is going to be matched to W tilde. Everybody else, can still match to their partners in mu. And if there were any blocks, right, we have a finite subset of the men and women from the original market. If there were any blocks, they would have been blocks in the original market too. Okay. If M tilde now submits W tilde preferred to null, well, if he's matched to W tilde under mu in this finite market, well, he'd better be matched to W tilde under the man-optimal stable matching. We don't know what it is, but he has to do at least as well as under some other stable matching in this market. And now we can use the strategy-proofness result in the finite case to know that M tilde has to do at least as well as being matched to W tilde if he reveals his true preferences instead.
Sorry,
Yeah.
Scott. What's the definition in the infinite case of man optimal?
It is a match, is a stable matching that all the men weakly prefer to all other stable matchings.
Now, that's not a finitary statement.
Correct.
And that doesn't generate any problem?
No, although again, here we're sort of implicitly using this fact that there's a highest ranked prospective partner. Right? It means that for any given set of stable matchings, for any stable matching, there's only like finitely many partners you might prefer to whomever you're matched to there.
Okay, so let me ask you, there is no existence in the infinite case, you don't know that such an object exists, right? A man stable matching.
Sorry, I mentioned that very quickly. So a generalization. So we actually, so Fleiner had a version of that result as well because it comes out of Tarski. Tarski implies like a lattice of fixed points, and so there's a man optimal and a woman optimal stable match. We actually also use a version of our logic approach to get there as well. So we have existence, but it's not obvious. I haven't explicitly shown you a thing that would get you existence.
Because for that somehow I don't see the finite. Again, you are comparing to what a man can get in all possible stable matchings, which I don't see how to express that with a finite formulas that are finite. So
that's yeah. So that is a trick. We don't state that precisely in a formula. Okay, sort of like this. We ask about sort of relative comparisons, and the sort of relative comparisons to a given object. So just like here, where we're asking like, is this man better off? You can ask for any given man, like, are you weakly better off, than some given fixed partner? And because the set of women you might prefer is finite, these become finite substatements. But like, find me a stable match and like look at sort of partners that might be better.
I'm sorry. That should only apply to all the W's with which you can be matched in some stable matching, which I don't know how to characterize. That formula is not doing the trick. That it's not true for any. It's just you are better off relative to all the women you can get in a stable matching, not a woman that you may not have gotten your top woman. Okay.
Yes. But again, if I fix a stable matching and compare relative to it, there's only finitely many such women you might be better off, that you might be better off matched to. So there could be potentially infinitely many women you are matched to in a stable match.
But you have to say there is no stable matching where one of those finitely many women, I get it. How do you state that? That's what I'm missing.
So if I start with any, so I propose we take this offline. I'll pull up the argument. We'll talk through it. But let me try one more time with the rough intuition. The rough intuition is if I start with any stable matching.
The rough intuition understood. My problem was this. But okay, sorry. Maybe you go on. Yes.
No. But if I fix any stable matching, so start with a baseline stable matching. I've proven that one exists. For any man, there are at most finitely many women that he might prefer to his partner in that stable matching.
You only look at stable matchings so now you start with, I see. Okay, so that's the answer. You start with the fixed stable matching that you got. Then you put every woman that is below that. You put it. You drop it below the line. Then you look at. Then there are only. Sorry, but it's still not finitely. But the number, since there are infinitely many men.
But each one gets a finite statement.
It's still infinitely many possible stable matchings, even in this restricted model. So I'm still
yes. But each man only gets a finite statement for each such.
But it's for all. But again, there is a quantifier for all stable matchings, and that's where I have my problem. Okay, go on. I don't want to detect.
Okay. Well, we'll talk about it in the sort of extended Q&A offline. It's a version of this type of approach. We basically, you reduce it to, you reduce the problem to, looking for each agent at a finite set of potential partners that they might prefer. Okay. Sorry, let me quickly review where we were in the where we were in the argument, and then we'll wrap this argument, and then spend a few minutes on couples, and then I'll quickly survey the other things we can do. So if M tilde submits W tilde preferred to null, then the man optimal stable matching is going to match W tilde to M tilde, which implies by the truthfulness in the finite case that M tilde had better be matched with W, and with some W weakly preferred to W tilde if he reveals his true preferences. That, remember, was precisely this statement. And so if our finite set of formulae happen to include that statement, we have just satisfied it as well. Compactness thus implies that the infinite set of statements is satisfiable. We've got a stable matching, the man-optimal stable matching, that has this additional property and satisfies it's stable, so it satisfies all the other constraints we already had, or all the other formulae we already had, and that implies that the infinite set of statements is satisfiable, getting us this claim. So M tilde does at least as well by reporting truthfully as if he submits instead W tilde preferred to null. And that means that there's no opportunity for manipulation in the infinite market. Questions there, because I know we sort of sidebarred in the middle of it.
Yeah, can you quickly explain why mu of W prime is not a subset of M prime?
Yes, definitely. So this is actually this is very important. So instead of just looking at M prime and W prime, we have to sort of carry over these other sets. And the reason they're not necessarily linked is because, mu of, we might have, for example, picked a bunch of formulae, targeting the men that are not matched to women in W prime, right? So we picked the set of formulae, not sort of with no relation to mu. Because we have to work with every finite set of formulas. So like, if I were an adversary, I could say, okay, give me W prime. Give me now a set of like 10 men that are, that are not matched to anyone in W prime. Give me a finite W prime, give me a set of 10 men that are not matched to anyone in W prime, and give me a finite set of their formulae. We'll call those the formulae.
Again, so
use this sort of argument.
So you start from taking an arbitrary set of formula and not set of you don't start from a marker like of a group of men and women.
Exactly. So to make compactness work, we have to be able to work with every set of formulae. And so we start with the formulae, not the market. Exactly right. And if we didn't construct this market from them, if we didn't sort of broaden the market, these sorts of statements might not be true. It might not be the case that mu would still be stable because like some of the partners would have disappeared. Restriction might not even be well defined. Great question. Further questions, queries, and so forth. All right. Okay, footnote. I mentioned already the lone wolf theorem actually fails in this infinite market model. And this is sort of like, a little wacky because we usually in finite markets prove strategy proofness by way of the lone wolf theorem. And this shows that in some sense, the lone wolf theorem is more brittle than the strategy proofness result. Like the strategy proofness result is somehow like more canonical or like sort of, it lifts to the infinite market, whereas the lone wolf theorem does not. Quickly, other things you can do with this machinery. A high school student of mine, Yunso Choi, showed that you can also use this machinery to, prove group strategy proofness, respect for improvements, and versions of the classical entry comparative static in infinite markets. She also at the same time showed, again, it's good to know that like not everything lifts in this way. The lone wolf theorem's example I just gave, it also turns out the classical weak Pareto optimality result, which is sort of the last with all the stuff on this slide plus the lone wolf theorem, is sort of the last like sort of early like main canonical matching result. I say this not to indicate that like a high schooler can use this machinery in general. Yunso is a completely extraordinary high schooler who's like already published multiple math papers. But it does, it does show sort of the breadth of applications you can use it in within like even sort of within the matching domain. Let me quickly broaden once more to couples matching. What's the setting here in the national residency match? Couples can submit their preference lists jointly. Existence of stable matchings in this context are not necessarily guaranteed, but Nguyen and Vohra have a beautiful near feasibility result that says in a finite many-to-one matching market with couples, we can find a stable matching with respect to a small perturbation of the capacity. How small? The capacity of each hospital. How small? Capacity perturbation at most 2. This is a totally different approach. They use Scarf's lemma and like rounding arguments. As a result, like it doesn't sort of naturally map to a Tarski-like approach. but it turns out we can actually like use compactness in almost exactly the same way we just did. So, we start with our old variables matched now DH for doctor hospital. We now add capacity HK, which is going to be a counting variable that sort of counts the capacity of a hospital H and says that it is equal to K. We're going to add some formulae that say, the capacity is within 2 of sort of its fixed, sort of baseline capacity. And it's well defined. So if capacity HQ, then not capacity HQ prime. And then, our usual matching formulae, right? Sort of nobody had better be matched twice. So it needs to be 1-to-1. And every hospital can't have more people matched to it than its capacity. So if its capacity is Q, then, and it's matched to Q agents, then it's not matched to doctors, then it's not matched to any others. We take all the other formulae, we condition them on the matching quotas.
Different than the DIs, yeah. For D different than the DIs.
For D different than the DIs. Yes, for sure. We condition, we introduce sort of conditionals on all of our other formulae that like you don't break the capacity. So a block can't break the capacity constraints and so forth. And we're done. Again, because we can apply the Nguyen and Vohra theorem in any finite such market, there's nothing else to do here in some sense. Like it's the exact as soon as you've rephrased the problem in the language of here, just like with our first existence rule, as soon as you've rephrased the problem in a way that sort of is consistent with the finite model and the language of the logic, sort of capacity can't move by more than 2. Well, the Nguyen and Vohra result tells us it doesn't have to move by more than 2. And all of these just lift directly by compactness. All right, we are very much running out of time. But let me just quickly run you through a list of other things we sort of have done with this technology, and I'll flash a couple of arguments on the slide for the sake of the recording if people want to pause it and look at the sketch of the argument. We have existence of stable matching chronologies with tenure and infinite past horizons. So this is we take a dynamic matching model that really very directly uses a date 0 and extend it and it goes infinitely in the future. But it constructs inductively from date 0. We show that you don't really need that date 0. So here's that. Boom. We reprove existence results for games and graphs under a local finiteness assumption, and give a similar argument for existence of Walrasian equilibria in infinite trading networks. Again, we need individual agents to sort of see a finite area of potential traders, but the network itself can be arbitrarily large. And again, we think of this as sort of a potentially better, infinite market model. The subtle or sort of limit market model. The subtlety here, of course, is that the objects in Walrasian equilibrium prices are continuumal, and we can't introduce continuumal formulae. So to do this, we actually have to grid the price space. And so what we show is that there's an approximate sort of equilibrium in this grid, and then we take the limit as that gridding gets arbitrarily fine. And then, as I mentioned, we can also do these decision-theoretic applications. We reprove the rationalizability of datasets satisfying GARP, a really, really beautiful theorem that Reny was able to prove generalizing Afriat. And then we use a similar method to give an infinite data version of the McFadden and Richter characterization of rationalizable stochastic datasets. Here is that setup. Again, we'll freeze for a moment for the for the recording. Boom. Reny introduced a really cool new elaborate argument, and we can give a very, very quick proof via compactness. As a bonus from that, there's a condition in Reny's argument that compactness turns out to actually need. And so this quasi-concave versus concave turns out to show up directly in the compactness argument in a way that's was certainly surprising to us how transparent it was. We were not expecting sort of the conditions of the theorem to pop out of the logic. So very quickly to wrap, probably 1 minute overtime. So we have shown how to go from finite to infinite in matching, trading networks, and decision theory, all in a unified method by way of logical compactness. As I said, we think of this as giving us sort of better models of large markets and dynamic steady states. and also sort of like exposing some surprising robustness to the results, like strategy-proofness and two-sided matching is somehow more robust than the lone wolf theorem that's typically used to prove it. And then, we didn't talk at all except for a couple slide flashes, but it also lets us think in the decision theoretic world about inherent limits of inference. It's a black box reduction. It's very easy to reason in, and so I hope we'll find other ways to use compactness. And please, if you guys come up with other approaches or other applications, let us know. I'd love to add more more examples to the slide. But phrased simply and sort of we should remember it in a meme. If you take nothing else from this paper, please remember, of course, that game theory is logical. QED.
Great, thanks very much, Scott, for the wonderful talk. So now we have strong evidence that not sleeping is not a problem for you.
Thanks.
So
I'll try.
We have time for some questions, if there are still any.